What if I told you every mountain on Earth used to be a tree? Not metaphorically, not some ancient legend, but a living organism, towering miles into the sky, wide enough that entire civilizations could have lived inside its trunk. Devil's Tower in Wyoming, the Matterhorn in Europe, Mount Roraima in Venezuela, they could all be fossilized remnants of trees so massive they make modern redwoods look like weeds. And if these mountains are stumps, then the forest they came from would have been unimaginably vast, stretching across continents, rewriting everything we think we know about Earth's history, its geology, and the forces that shaped our planet. The theory has millions of believers. And when you look at Devil's Tower, rising 1,267 feet above the plains of Wyoming, it's hard not to be intrigued. Those perfectly hexagonal columns look almost too geometric, too structured to be natural. The official story is that it's a volcanic intrusion, magma that cooled underground, cracked into those striking columns. And then, over millions of years, the surrounding softer rock eroded away, leaving the tower standing alone. But advocates of the ancient tree hypothesis push back. They claim those columns aren't just cooling cracks, they are fossilized cellular structures, the very veins of a tree trunk frozen in stone. The flat top? That's where it was cut. The debris around the base? Bark and branches that fell away as the stump petrified. Look at it without geological training, and it almost seems plausible. Even on a smaller scale, petrified trees show columnar patterns that echo what we see here. The origins of the theory go back to a Russian researcher in the early 2000s, cataloging formations that seemed too symmetrical, too uniform, to have been sculpted by chaotic erosion or tectonic forces. He studied flat-top mesas, hexagonal columns, mineral compositions, and asked a provocative question. What if we've been interpreting these structures entirely wrong? His hypothesis was that Earth once hosted trees that grew miles tall, supported by an atmosphere radically different from today's, maybe with higher oxygen levels, maybe even lower gravity. Forests that enormous would have dominated the landscape, controlled weather patterns, and shaped erosion in ways we can barely imagine. Then came the cataclysm. Some suggest a meteor impact, others atmospheric shifts, and a few even invoke the intervention of intelligent beings. Whatever the cause, these giants fell, and over millions of years, their organic tissue mineralized, petrified, and became what we now call mountains. Yet here's the catch. Petrification doesn't scale like that. Organic tissue is replaced cell by minerals, a process that works for trees, bones, shells, but for something the size of a mountain, the internal pressure, heat, and sheer mass would collapse the structure long before petrification could finish. A tree miles high would rot and crumble. Geologists point out that Devil's Tower's mineral composition aligns perfectly with cooled magma, the crystals forming only under conditions of volcanic flow. Surrounding geology supports the intrusion model. There's no missing piece. The puzzle fits the volcanic explanation. Still, proponents aren't just dreamers. Engineers, architects, material scientists, they question whether our understanding of petrification is limited to modern conditions. What if ancient atmospheric pressure, chemical composition, or biological processes allowed petrification on an unprecedented scale? They point to the Giant's Causeway in Northern Ireland, basalt columns in Iceland and Scotland, repeating patterns across continents, and ask, why does this geometric symmetry appear everywhere? Could there be a biological template we've overlooked? Mount Roraima in Venezuela offers another case. A flat-topped mountain rising abruptly from dense jungle, sheer cliffs on all sides. Geologists classify it as a table mountain, a tapui formed by erosion of surrounding softer rock. But the ancient tree advocates highlight the almost perfect flatness of the top vertical cliffs and a debris field with unusual mineral ratios. Even more intriguing, the plateau hosts species found nowhere else, as if they evolved in isolation atop a once-living structure. The official explanation: species evolved after the plateau formed. The tree hypothesis: they are remnants of an ecosystem that lived in the canopy of an ancient forest. Now, imagine the scale. Devil's Tower is a stump, 1,267 feet tall. Based on modern trees, where stumps are 10 to 20% of total height, the original tree could have been 6 to 12,000 feet tall over 2 miles. Hyperion, the tallest tree alive today, reaches 380 feet. These would be 30 times taller. Mount Roraima is 9,220 feet tall. If that's a stump, the tree might have been 9 to 18 miles in height, higher than commercial airliners fly, reaching into the stratosphere. Apply this logic globally, and some ancient trees could have reached the edge of space. Believers have cataloged dozens of potential stumps. Brand Mountain in Namibia, Mount Connor in Australia, Tapui formations across Venezuela and Brazil. Each looks like nature cleaved off the top of a colossal trunk. Geology offers explanations: granite intrusions, mesas from erosion, massive sandstone plateaus carved by time, stratigraphy, and mineral studies back these conclusions. Yet tree theory advocates insist: why so many flat-topped mountains? Why the recurring symmetry? Isn't it too consistent for random erosion? Geologists explain it clearly. Flat tops form when a hard, resistant caprock shields softer layers beneath. As the surrounding terrain erodes, these plateaus remain, eventually standing higher than their surroundings, sometimes isolating into mesas. This process is documented across the Colorado Plateau, where erosion unfolds over geological time, a slow but relentless sculptor. But proponents of the tree hypothesis refine their claims. They aren't suggesting all mountains are ancient stumps. They focus on formations that seem incompatible with the erosion model. Many of these flat-top mountains maintain remarkably consistent heights within a region, as if deliberately cut at the same level. They scrutinize the mineral composition around these formations, claiming the ratios resemble decomposed organic matter more than eroded rock. The hexagonal columns, too, provoke debate. Hexagonal jointing forms naturally when lava cools and contracts, creating the most efficient fracture pattern, hexagons. It's a geometric inevitability of thermal stress. Yet, biological structures also favor hexagonal packing, the most efficient way to organize cylindrical cells. Honeycombs, plant stems, even some tree trunks reveal this pattern under a microscope. Believers argue that these repeated geometric signatures might hint at a biological origin rather than a purely volcanic one. Physics and biology, however, impose hard limits. Trees rely on capillary action and transpiration to move water. Gravity sets a ceiling. Under current atmospheric pressure at sea level, water cannot rise more than about 400 feet through passive transport. Trees taller than this face systemic failure. Advocates of mile-high trees point to past atmospheric conditions, noting that during the Carboniferous period, oxygen reached as high as 35%. Giant insects existed then, dragonflies with 2-foot wingspans, millipedes the size of cars. But oxygen alone doesn't make trees taller. Water transport, not oxygen, limits height. Capillary action and negative pressure from transpiration can't overcome gravity beyond the 400-foot threshold. Even if atmospheric pressure had been higher, the effect would be insufficient. Supporting a tree miles high would require pressures far beyond anything evidenced in the geological record. Some suggest gravity itself was weaker in the past, allowing colossal growth. Fringe theories propose Earth's mass increased over time, gradually strengthening gravity. If gravity had been half of today's trees, could theoretically reach twice the current height limit. But all credible measurements contradict this. GPS, tidal studies, orbital mechanics, lunar observations, they confirm Earth's radius and mass have remained constant for billions of years. If gravity fluctuated dramatically, fossil structures, impact craters, and the moon's orbit would reveal it. They do not. The fossil record aligns consistently with today's physical laws. The tallest land animals ever, the sauropod dinosaurs, demonstrate what's physically possible. Their massive bones, air sacs, and reinforced leg structures pushed the limits, but they didn't exceed them. Trees, constrained by the same physics, could not have been miles tall. Fossils from the Carboniferous period show enormous trees, yes, but the tallest reached roughly 150 to 200 feet, well within the scale of modern conifers and eucalyptus. Mile-high trees remain implausible biologically, physically, and geologically. Believers counter with myths. Across cultures, legends speak of immense trees connecting Earth to the heavens. Norse Yggdrasil, Hindu cosmology's cosmic tree, Native American stories of a great tree felled by gods or giants. Could these be cultural memories of real giants? Anthropologists explain these as archetypal symbols. The tree represents life, growth, connection, a universal metaphor. The recurrence of such myths worldwide reflects humanity's symbolic thinking, not physical evidence. Yet proponents push harder, citing precise details in these legends. Trees cut down, stumps remaining, a world before their fall. They argue, if these are mere myths, why such consistency across disconnected cultures? They invoke advanced pre-human civilizations, extraterrestrials, or giants as agents capable of felling such titanic organisms. The flat tops of mesas and stumps, they claim, are proof of deliberate cutting, not natural erosion. Mainstream geology offers a simpler answer. Volcanic intrusions, tectonic uplift, differential erosion explain flat tops, vertical cliffs, and hexagonal columns. No rewrite of physics, chemistry, or biology is needed. These are processes we can measure, model, and observe. But here's the nuance. Science has been wrong before. Continental drift, once dismissed, became plate tectonics. Meteorite impacts, once thought impossible, explain the KT boundary that ended the Cretaceous. Questioning assumptions drives discovery. Believers point to formations, symmetry, scale, mineral anomalies, myths, and biological possibilities under alternative conditions. They argue that science doesn't have all answers, and perhaps the consensus overlooks something extraordinary. But extraordinary claims require extraordinary evidence. And the evidence for mile-high trees is speculative at best. It rests on multiple assumptions: higher oxygen, lower gravity, unknown petrification processes, lost civilizations, or catastrophic events, leaving no trace. Layer upon layer of assumptions accumulates, demanding heavier proof. Accepting this would mean rewriting geology, physics, biology, and chemistry, all to accommodate a world that contradicts everything we reliably know. But let's entertain it for a moment. Suppose it were true. Suppose Earth once hosted forests of mile-high trees. What kind of planet would that have been? The canopy would have pierced the stratosphere. Weather patterns would have been unrecognizable. Rainfall might have been trapped in upper layers, creating rivers flowing through the branches before ever touching the ground. Light at ground level would have been perpetually filtered, dim, almost twilight. Ecosystems would have stratified along the vertical expanse. Birds, insects, mammals, each adapted to a distinct layer. The trunks themselves would have been entire habitats, species moving up and down the bark, never reaching the forest floor or the canopy extremes. Roots sprawling like city networks, delving deep into the crust for nutrients, anchoring these colossal beings against winds capable of toppling modern skyscrapers. Imagine living in such a world. Lower levels, dark, humid, dominated by slow decomposition and fungi. Middle layers, enough light for understory plants, animals navigating partial sunlight, shielded from the extremes above and below. Upper canopy, constant winds, intense sunlight, temperature swings, life specialized entirely for that altitude. Evolutionary pressures in each zone would have been distinct, producing biodiversity beyond comprehension. The trees themselves, if biological, would need extraordinary adaptations. Trunks strong enough to support miles of growth, vascular systems moving water and nutrients vertically across unimaginable distances, root systems anchoring against winds of immense force, bark thick enough to shield from extreme temperature gradients. Some theorists propose silicon-based biology, organisms integrating minerals as they grow, partially mineralized while alive, explaining their petrification. But silicon life is speculative. We have no evidence it has ever existed on Earth. Silicon bonds, while similar to carbon in some respects, lack versatility and stability for long chains. Biochemistry models for silicon-based life run into structural impossibilities. Even if these forests fell, ecological collapse would have been catastrophic. Sunlight exposure, loss of canopy rainfall, billions of tons of decomposing biomass releasing carbon and methane, an extinction event dwarfing the dinosaurs. Such an event should leave a clear boundary in the geological record, a distinct layer marking a sudden ecosystem shift. The KT boundary from the Cretaceous asteroid impact shows exactly that. But for these hypothetical mile-high trees, no such boundary exists. Sedimentary records show gradual shifts, predictable erosion, no abrupt collapse indicators. This is the central problem. The theory demands rewriting not just one domain of knowledge but multiple: biology, physics, geology, chemistry. For such a radical theory, evidence must be ironclad. So far, it is not. Formations that resemble stumps have conventional geological explanations. Myths reflect universal symbolism, not literal memory. Physics restricts water transport and structural support, limiting tree height. Fossil records confirm these constraints. Still, the imagination persists. Even if the trees weren't miles high, Earth's past was remarkable. Carboniferous forests were alien. Oxygen levels higher, insects enormous. Continents arranged differently, climate warmer. Fossilized trees already astonish with size. That's wonder enough. The real story of Earth's evolution is strange, complex, and beautiful, without inventing cosmic forests. Yet for those who see Devil's Tower as a stump, Mount Roraima as a cleaved trunk, or question what geologists might have missed, there's a challenge. What evidence would convince you otherwise? What could overturn this belief? If the answer is nothing, if no geological or biological analysis could change your mind, then it is not inquiry, it is belief. And beliefs, unlike theories, need not be proven. They only need to feel true. So we are left with a world full of questions. Mountains that look like stumps, myths of cosmic trees, a theory compelling in imagination but lacking definitive proof. And in that gap between fact and fascination, wonder remains, a reminder that Earth's history is stranger than we often allow ourselves to imagine. Kermone Band, Dalarng Ngay. Comment, like, subscribe, nếu thấy hữu ích hãy góp ý cho chúng tôi.